All right, so for comp 3, it's all about these titration graphs, and then we're going to be doing calculations along different points of these graphs, where we're looking for pH or the moles titrated. So this is supposed to represent a strong acid and a strong base. You can see each one. Strong acid, weak base, weak acid, strong base, and then don't worry about this one. Okay, so we're going to focus on these three. To remind you of some things from Chem 1, the equivalence point pH can indicate to us which of these scenarios we have. And so let me just remind you how to find the equivalence point and why that is. So there's going to be a vertical portion on each titration graph, and if you go midway, that is called your equivalence point. And that's where moles of your hydrogen equal moles of your hydroxide. And so essentially your acid and your bases have neutralized. And so the only thing that determines the pH here is the products. And so strong acids and strong bases make salts, neutral salts, and water. And so that's why our pH is at 7. When I come over here, my equivalence point is down here. So you'll see how it's below 7. That's because strong acids and weak bases, I'll give you an example, HCl and NH3, they are going to create things where the acid gives away a hydrogen, like this. Chlorine's negligibly weak, and that is an acid. So that's why our pH is below 7. So never say the reason is because one of our reactants. It's always because of the products they produce. And so if your equivalence point is below 7, it's a strong acid and a weak base. But why is the pH below 7? Because of the salt they create. And then over here at our equivalence point, we can see midway through the vertical line, it's above 7. And so that's going to tell you you have a strong base and a weak acid. So if we had NaOH plus a weak acid, I'll just do HF. Our products will be water and then the salt NaF. We would ignore Na, it's negligibly weak, and right there, that's a base, right? It's a basic salt. And so the pH above 7 tells us we have a strong base and a weak acid, but why? It's because of the products. And then we won't be doing two weak things. There's some other points on your graphs that you need to be familiar with. So the two with weak things in them can also have buffering regions. We learned about buffers in the last video. It's where we resist change at the pH. So it's usually at the front end where it's really doing its best not to change pH. We would never call these at the end a buffer region because this is just, it's flooded. This thing is not a buffer region. It's not, buffers aren't going to be made from two strong things, so we're not going to call that a buffering region. Something new this year is your halfway equivalence point. So I wish these had numbers for volume. Let's just pretend that this took 20 milliliters down here. So your halfway equivalence point would be, well, what's half of that? 10. So right here, right? You're halfway to the equivalence point. All right, so on this one, the halfway looks about here, but it's best if we had milliliters to go off of the x-axis. Your halfway equivalence point, maybe about right here. And so this is nice because this can help you identify the weak acid or the weak base. So if I'm here at the halfway equivalence point, two things are true. pH equals pKa of your acid, or POH can equal pKb of your base. And so now if they're like, hey, what base are we using right here? You would say, okay, well, pH 8, 9, let's just call that 10. We would say, okay, well, pH is 10. So POH is 4, because they always add up to 14. And now what you could do is, since you know pKb is 4, you could solve for Kb. It's 10 to the negative 4th. And then they would have a list of Ks of all your bases, and you could go find the one that matches. And so now we have a way to identify what we're titrating with. Same over here. Even if your halfway equivalence point's down here, these two things are true at any halfway equivalence point. You want to use this one if like you're in the base, looking for a base, and you want to use this one if you're looking for an acid. The last thing I think, if I think of more, I'll come back to it, but is you are going to be asked like, hey, what indicator should you be using? And so what you want to do is you want to focus on what's the pH at the equivalence point. So if I know I'm titrating a strong acid with a weak base, I should know, okay, the equivalence point is going to be below 7. So in my list of indicators, which will be given, and what colors they change and what range they change in, I would look for one that changes at a pH below 7. So I know when to start stopping my titration. If I am looking for this one, right, I would look for an indicator that starts to change above 7. So keep that in mind. If you remember from last year when we titrated, indicators change colors when your pH changes. And so you're looking for one that changes around this point. So now we're going to go in, you're going to be asked all kinds of questions about these. If you feel like I didn't cover something, feel free to email me. But you also might see curves that look like this. And what you're going to do from this is just identify acids from it. Bases, well, let me start here. Each vertical line is an equivalence point. So halfway here, this is our equivalence point 1, equivalence point 2, equivalence point 3. And so this is where we are neutralizing our different hydrogens. So whatever acid this is, it must have had 3 hydrogens because we neutralized 1, 2, 3. So maybe it's something like this. That's the extent of these. This is called a triprotic curve that you need to be able to answer. Let's say you had a titration curve that looked like this, right? Say, okay, there's equivalence point 1, there's equivalence point 2. So this would just be something with like 2 hydrogens. But most of the curves you're gonna look at just have that 1 equivalence point. And it could be in either direction, but just 1, right? These are the ones you'll have to do most of your questions on, but these, just look for the number of equivalence points you see is the number of hydrogens your acid should have. Okay, in addition to answering questions on titration curves, you're also going to have to do calculations, and these are still along a titration curve, we just don't have a graphic to go off of. So in this question, we have 165 milliliters of 0.22 of this strong acid. It's titrated to the equivalence point with this strong base. After reaching the equivalence point, so remember the equivalence point, your hydrogens have canceled out with your hydroxides. That's where they're equal, and so they all went and made water. So when you have this strong acid and this strong base, at the equivalence point, our pH should be 7. But then it says you are going to add 6 more milliliters of LiOH. So this is a base, strong base. So since all of this is gone and all of this is gone, right? These two have neutralized, and then we add this. Whatever our pH is, it should be above 7. So at this point, if this is a multiple choice question, go get rid of 7 and anything below. We're adding base to a neutral solution, so it's got to be a basic pH. So we know we need molarity of this thing, right? What we're going to do, our game plan, pH is going to be 14 minus POH. The reason I'm saying that is because I have a base. POH is the negative log of hydroxide. And I don't need an ice table because this thing is strong. I don't know why I wrote strong acid. That's a strong base. Okay. So I need to find the molarity of hydroxide. And so that's what I'm going to do. Now, hydroxide is going to be moles over total volume. All right. when I look here, I know molarity of lithium and I know the volume of it, so I can find the moles that I added. So I can say 0.006 liters times the molarity, that's my moles. For total volume, I know that I added 0.006 liters to 165, but I'm turning to liters of the acid, but I also had liters of this base. I don't know how much it is. So that's what I need to go and find here. And then I can start doing these steps. All right, so I am going to go find the volume of this so that I have total volume at the end. So our moles of acid and base are equal at the equivalence point. There's a couple ways we can do this. The first thing I'm going to do is I'm going to use this formula to find the volume of the base. You might remember this from Chemistry 1. This can only be used for a strong acid plus a strong base at the equivalence point. Which is perfect because that's what I need. I need to know how much of this strong base I used at the equivalence point. And so my molarity of my acid is 0.22. Volume of my acid, I can leave in milliliters. Coefficient, I can tell you already they're going to be 1 because everything in this has a 1 charge, but just to prove it to you, that's my formula and it's balanced. Molarity of my base, 0.17. Volume of my base, coefficient of my acid. So I'm going to find my volume of my base and then go plug it in right here. 213.5 milliliters. So plus 0.2135. All right, so let's get that molarity of hydroxide. Take the negative log of it, 14 minus. Okay, so when I did my moles, molarity times liters of my hydroxide that I added in at the end, over my total volumes of everything, I got a molarity of 0.458. And so since it's lithium hydroxide, it makes 1 hydroxide. That's the molarity of this. POH is negative log of 0.458. And that gives me 0.339. But the question wants pH, and so before we said it should be above 7, so that one it makes sense. So 14 minus that, our final answer is 13.66, and that makes more sense. All right. Go over it again if you need to know where the numbers come from, or if you get stuck on one, make sure you email me. Let's go to the next question. All right, here's the next kind you might see, and usually I feel like these are pretty common on tests. We are finding the pH. We have this strong acid, and it's titrated with this strong base. And so you might be thinking 7, and 7's probably going to be an answer choice, but look at the hint. It is not at the equivalence point. So when it is not at the equivalence point, find out which one you have more of. But let's compare moles, because they don't have the same molarity, so we can't just look at those numbers. So we're going to find moles of HCl. We're going to do molarity times liters, so 0.12 times 0.055. We'll get that one. We're going to compare that to moles of the base, KOH. And so we're going to do molarity, 0.05 times its volume, 0.082. And so let's get moles of both of these, and then we'll see which one we have more of, which will determine our pH. So at this point, once you have moles of each of them, the one that you have more moles of, so in this case it's the acid, that will tell you what the pH should be. So y'all, when we're done, our pH should be below 7. So you're canceling out any numbers that are 7 or above. And so every time you have one of these, it's going to react with one of these. And so the way this determines the pH is it's going to take out the 0.0041 moles of potassium hydroxide are going to take out 0.0041 moles of HCl by reacting together. So we're going to have leftover moles. So that's what determines pH. So if we subtract these, that will give us our moles of acid that still have the capability of changing our pH, because the same number of moles are going to react and neutralize. So I'm going to go ahead and subtract, and that's how many moles of acid we still have that can go and mess with the pH. And so in order to find pH, we need to take the negative log of hydrogen concentration. So we're going to say the negative log, and hydrogen concentration is moles. Well, we just found that 0.0025 over liters. And just make sure you're adding total liters because they're both in there. So 0.055 plus 0.082. All right, and so this will give us molarity of hydrogen, and we'll take the negative log of that, and that'll be our answer. And it should be below 7. I'm getting 1.74 pH. All right, our last question. How many milliliters of strontium hydroxide do we need to titrate this milliliter, this molarity of the diprotic H2SO3 to the second equivalence point? So I don't know if you remember this, it's been a while, but every time an acid can give away multiple hydrogens, it's going to have different Ks for it. So the first Ka will be for the first hydrogen it gives away, and the second Ka will be for the second hydrogen. This one is so incredibly small compared to the first that we ignored. And we're going to kind of do the same thing here. We could take the time and we could find how many milliliters it takes to get to this second point, but it's going to be so incredibly close to the first that it's negligible. So don't let this kind of throw you for a loop. We're just going to focus on the first one. All right, so at the equivalence point, our moles are equal. So I'm going to first find moles of our acid. So moles of H2SO3 is molarity times liters, 0.06, and we get, all right, so I'm going to work that from moles of the acid to moles of the base. I'm going to go ahead and get a balanced equation so I can do that. So strontium hydroxide, Sr, plus sulfurous acid, we'll always get water, just double replacement reaction, and salt. And it just kind of looks like I need a little 2 right here, and I think I'm good after that. So 0.0066 moles of the acid to moles of the base. And so you can see it's a 1-to-1 ratio. I kept writing a 4, but that's a 3. 3, sorry. To the base. We're gonna get the same thing. And you could also do a Stroik chart, moles to moles. All right. So now I know that's how many moles of the base I'll have at the equivalence point. If I want to know volume of this, we've rearranged the molarity formula. It's just moles over molarity. So I'm going to take my moles, I'm going to divide by molarity, and then that's going to give me liters. And I'm sure it would ask us for probably milliliter. Oh yeah, it does say milliliters. So there we go. And don't worry about that second equivalence point. I'm telling you, it's going to be so close to this number. It's going to take that, or that'll be an answer choice.